Hi guys, BuildZoid here, and today we're going to be taking a look at a motherboard that is not relevant and it's not new, but I think it's cool, and that's why we're taking a look at it. So this is the Gigabyte Z270X-Gaming 9. This is Gigabyte's flagship for the Z270 platform, and this is one of those motherboards, like back in the day, I didn't yet do videos like this, so that's why I didn't make a video about it when it was relevant. Yeah, this is a really cool board because this is one of those ridiculous Gigabyte, flagship motherboards where it's kind of, well, that should give you that alone should be enough to tell you why I'm interested in talking about this board. Also, we've got this chip right here, which this is a PLX chip. So basically what this does is a PCIe switch. So it'll take the 16 lanes between your 16 PCIe lanes from the CPU, and it'll actually be able to split them up. It's not like it gives you virtual 32 lanes. So if you're not using all of the band, let's say, no, that's not a good, basically it's a switch. So you still only have 16 lanes worth of bandwidth, but now you can take that bandwidth and split it between 32 lanes worth of devices. So as long as you're not actually trying to use 32 lanes worth of bandwidth, this works really well because you basically get a lot more flexibility in terms of what kind of things you can hook up. Like you can hook up 4 GPUs at once because they'll each have their own 8x connection, as long as they don't try to, well, actually GPUs don't need 8x. It's just kind of an artificial restriction of NVIDIA's SLI, where it's just like, if you don't have an 8x PCIe slot, we won't enable SLI, which is dumb. But the funny thing is if you look at Crossfire will actually run off of X4 slots, or at least on the older drivers it would. I don't know if they added a restriction like NVIDIA has. But the thing is, it can be useful. Let's say you have, I don't know, an M.2 expansion card with 4 SSDs at once, and then you also want to have, say, 2 GPUs for SLI, then you can actually have, if you're not using the GPUs because you're just sitting on desktop, copying files around, then you can actually use the full 16x PCIe slot bandwidth for the M.2 card and not use, because the GPUs aren't currently really using any of the PCIe bandwidth, so you can get the full bandwidth of your M.2s. And then when you start playing a game, well, as long as you're not also trying to copy giant files in the background, you get all of your PCIe bandwidth for the actual GPUs. So pretty cool that you can basically reallocate. Basically, it makes your PCIe lane allocation much more flexible. There is one downside to these. They're expensive. They run kind of hot. Well, actually, there's a couple downsides. From the board vendor's perspective, they're expensive. Back in the day, the chip was like $50. These days, it's more like $80. Don't ask me how that works. But yeah, the chip recently, the reason why it's rare, the chip is kind of rare these days is because it did get more expensive. But it also runs rather hot, so you do need a more substantial cooling system on the motherboard if you're going to have a PLX chip, and also they do add a little bit of latency to the PCIe communication. Now, Gigabyte has a motherboard where they actually work around that really cleverly, where they have one PCIe slot where if you're running single GPU, it only uses, it completely bypasses the PLX chip. But if you're running multi-GPU, you actually go through the PLX chip, because in multi-GPU, you don't have enough PCIe lanes anyway, so it's not really an issue. And in single GPU, it's nice that, hey, you don't have to hit the PLX chip yet. So you don't get that latency hit that the PLX chip adds. It's not a huge hit. It's just it's measurable, but it's not very significant. It's not something that you would notice it if you were playing games, but it is there enough that it affects benchmark scores and that kind of thing. So anyway, I think that's really, that's a really cool chip. Other than that, we've also got a power button. We've got a bunch of buttons that aren't worth pressing, because this is basically OC mode. That's just a bad overclock profile, and that's a bad power saving profile. So just don't use those. You've got a clear CMOS and reset button as well. I don't know which one's which though. It doesn't really matter. You just look at the board if you have one, right? But the important thing is that both of those buttons are present. It's not important which one's which. You've got 2 postcodes, which I'm actually not sure what the second one is for, but hey, 1 postcode is good. 2 postcodes can only be better. I can't think of a way they could make it worse, right? What are you going to do? Yeah, no, I really can't think of a way that 2 postcodes could be worse than 1. So yeah, 2 postcodes, which is kind of neat. And even though it's probably for voltage monitoring or something, which is Like the funny thing is, my opinion on built-in voltage, like unless you do what Asus does with on their more modern motherboards, where they have an op amp replicating the core voltage, like the actual DiSense voltage to the Super IO and everything else. Like, unless you're doing that, you may as well not bother. Like, it's totally like, because your voltage reading is just like, oh, it's from the CPU socket, and on the high current draw CPUs, it's just like the voltage drop across the socket is absolutely insane. So it's just like, well, that's a really useless voltage measurement, isn't it? Anyway, so it could also be for, well, no. Well, it could be for temperature monitoring as well, I guess. But anyway, I've unfortunately not yet had a chance to power this motherboard on. I've had it for a while, but it's just been kind of sitting in its box. Though I did actually swap all the... So normally this motherboard comes with like a white plastic I/O cover, and the chipset heatsink has a white highlight instead of a black one. But Gigabyte uses the same chipset heatsink for their X370 motherboards as for the Z270 board. So I just swapped the nice black heatsink off of my X370 board onto this thing, because the white one was ugly in my opinion. So yeah, and I also did the same for the I/O cover. So I have like a blackout version of the Gaming 9 instead of a white version. So I much prefer that. Looks better. Anyway. Next, we've, of course, like, this is a high-end Gigabyte motherboard, so, of course, it's got dual BIOS as well. You've got LEDs to indicate which BIOS chip is active. And then, because Gigabyte's automatic dual BIOS system gets in the way when overclocking, you also have a switch to put the motherboard in single BIOS mode, and then a switch to select which BIOS chip you're on manually. So that's very handy if you're overclocking any high-end Gigabyte, well, any Gigabyte board, and they kind of keep it exclusive to the high-end ones because, well, it costs money to add, you know, this kind of functionality. So I'm not really a fan of the fact that, like, Gigabytes, like, low-end Gigabyte motherboards with dual BIOS are just kind of annoying, because you need to save all of your BIOS profiles onto, like, a USB stick. Otherwise, every time the motherboard decides that it's crashed too many times in a row, you lose all of your profiles, which, like, you don't lose them. They're just on the other BIOS chip, and since you just got switched to the, like, if they're on your main BIOS chip and you got switched to the backup one, well, you can't get to your profiles, can you? So that's why you need to use a USB stick with lower end motherboards to save your like low end Gigabyte boards to save your profiles, which is just like, that's dumb, Gigabyte. That's really dumb. Like, the other solution would be if they just included some flash storage on the motherboard for saving profiles outside of the BIOS chips, because it's just so annoying when it's like, oh yeah, I like, it's either this or a USB stick. So yeah, then we have some switches over here, but as far as I know, these are for some audio thing, and I don't care about the audio section on motherboards. Also, they have like replaceable op amps on this one, but it's just like, I don't pay attention to audio, so there's really nothing I can tell you about this. It's just like, well, that's a thing. Don't know if it actually does anything useful though, but it's there. So considering that they no longer do this on their more modern motherboards, I assume this wasn't actually that useful, because they decided to not bother doing it anymore. Anyway, I think that kind of covers all of the general overclocking features. I expect a comment about, hey, Buildzoids, what's the turbo B clock thing? So this is just an external clock gen, and you get this on basically any higher end Z170, Z270, Z370, Z390 motherboard. You're gonna have a clock gen, and higher end X470s, X370s, and X570s motherboards also have external clock gens. And the point of having an external clock gen is you get either finer adjustments in terms of BCLK and much more BCLK range, so you can push the BCLK much lower and much higher. And you can also, well, it gives you also options to like adjust the actual signal parameters of the BCLK as well, which can sometimes help with overclocking. But the thing is, on Z270 and Z170 motherboard, well, Z170, like, all of the LGA 1151 CPUs have their BCLK decoupled from things like your PCIe and SATA, so you can actually push the BCLK to absolutely ridiculous frequencies. I think the record for Z270 is something like 400 megahertz of BCLK, which is absolutely insane. Now, there's a reason why you don't really hear people talk about this too much. It's not very useful, because Intel actually restricted the BCLK overclocking range for everything except K CPUs. So if you have a non-K CPU and you increase the BCLK past 103 megahertz, the system will not allow you to post. So, you know, it would be like, oh, with an external clock gen, I can overclock my non-K CPU. No, you can't. Intel doesn't want you to do that. But if you do have a K CPU, you just, with an external clock gen like this, you get insane BCLK range. And that can be helpful. Like, the thing is, Z270 as a platform has a very limited range of memory multipliers. So here it actually helps if you're trying to push past, like, I think it's 4133 megahertz on a 7700K. That's the, like, last ratio that you actually have. That works. The 4266 I think is available, but I don't think it works. It's been a while since I've last run my 7700K. So if you don't have the turbo, if you don't have like a way to extend the BCLK range, you're kind of screwed. But if you do have an external clock gen like this, you can actually go and push like 110, 120 BCLK, or like you can just push as much BCLK as you want basically to try get, you know, higher memory speeds. So that's why this was useful. Funnily enough, they've dropped like most, actually, like ASRock used to call it hyper BCLK. I don't think Asus really ever did a big marketing thing around it, but Gigabyte did the whole turbo B clock, you know, cover over it. And this was just done because going from Z97 to Z170 and LGA 1151, it was new that you actually had a BCLK range that wasn't completely bloody useless. Because on Z97 and such, like, you couldn't really push the BCLK more than like 7%, 10. Well, I think the upper limit was around 10% or something. But generally, even just hitting 7% was like really sketchy. And then if you kept pushing past that, it would cause all kinds of issues, because on those platforms, it would overclock your SATA, it would overclock your PCIe, and your GPU would flip, your hard drives would flip about it, everything would complain. So it really didn't work that well. But with the LGA 1151, it was like, look, guys, BCLK overclocking is back, except it's only available on K CPUs, so it's not actually that useful. But hey, we did get, you know, these fancy clock gen covers on Gigabyte motherboards for it. So anyway, that's what that is. Now then, let's talk about the power delivery. And there is a lot of it. And the funny thing is, it's actually all this, like, it's the same chip over and over and over again. So let's start highlighting, because there's a lot to highlight. So this VRM is basically like the most brute force VRM design I can think of. So this down here is your PLX. That powers the PLX chip. So we're not going to really talk about that, because it's like, you're not going to overvolt your PLX chip. There's no point doing that. So yeah, this just kind of exists, and it's good that it exists, because if it didn't, the PLX chip wouldn't work. But that's about as much as I care about that VRM. Then here we have either the IO and the, well, one of these, so these two, and I'm failing at highlighting that properly. I should have started on there, right? Like that's the smart way to do it. So one of these is IO and one of these is SA. I'm not sure which, but I'm going to go like SA and IO and hope I have them in the right order. They might be flipped. It doesn't really matter. They're the same power stages in both. And they're also on the same controller. So it doesn't really matter if I have the order wrong, because they're physically, like, the components in each are the same. Then all of this, all the way to here, is vCore. Yes, that is a hell of a lot of vCore. And this is kind of why I really want to talk about this board. And then over here we have the iGPU VRM, which is just like, you know, like, this is a little bit too much board space dedicated to a voltage regulator that on a 7700K you're probably going to have turned off, right? Like, realistically, are you actually going to do anything with your iGPU on a 7700K? This is 7700Ks, if I remember correctly, did not yet have a quick sync. So it's not like there was any reason to have the iGPU active if you had a dedicated GPU, which if you're buying a 7700K, you'd have, because that was like the top-end gaming CPU from Intel at the time. So yeah, I'm not sure why I'm referring to 7700Ks like they're super old. They're not really super old, but still, it's just like, but it is just a quad core, which is kind of crazy to consider that suddenly, like, and now suddenly quad cores aren't cool anymore. When, you know, it's been the reign of the quad core for who knows, like, yeah, like, it's been like for years and years, it was just like the best gaming CPU from Intel was a hyper-threaded quad core, and you couldn't get anything else, and now it's like, well, not cool anymore. Anyway, so yeah, that's the iGPU power over there. Let's talk about the V-Core, because the V-Core is awesome and huge and insane and ridiculous. So the thing is, I actually am not sure which of these two chips right here is the V-Core VRM, because Gigabyte, in their extreme, like, this board is just ridiculous on so many levels. Like, well, this is part of the ridiculousness of this board. Both of these are IR 35201s. IR 35201s are 8-phase voltage controllers. Why is there two of them? Normally, even on high-end motherboards, you'd see only one. Well, there's only one way to get a 16-phase V-core out of a 35201, and that's if you run your 35201 as an 8 plus 0, like, if you run it as an 8 times 2 plus 0. And that's exactly what's going on with the V-Core one, which I think it's the lower one that's V-Core, just because it makes more sense to have your iGPU one closer to the actual iGPU. And yes, the other one is entirely dedicated to the iGPU and running as 4 plus 0. So, yeah, V-Core is 16 phases, and iGPU is 4. And it is very much just running just 4 phases of iGPU. As in 4 plus 0. So that's great. Like, they're using half of one of these controllers to just generate the iGPU, and that's it. Anyway, the way they're getting that 16 phases, the 16 phases on the V-Core is, of course, it's not anything particularly special. We've seen it 1,000 times before. It's an IR 3599 doubler, of course. So those double, they quadruple. They're running as doublers here. They don't current balance, but the IR 35201 and other high-end international rectifier controllers are actually smart enough to still distinguish between two phases even after the doubler. So effectively, this runs like a 16-phase. The only downside is the 3599 adds a little bit of delay to the PWM signals, which does have does negatively impact the transient response capabilities. However, also in my testing with Z390 and Z370 motherboards, that doesn't really seem to matter too much. Like, the impact isn't significant enough to really make it, like, there's ways to design the VRM that just completely negates any effect the 3599 has, so you don't really need to worry about it. Though I don't, and the thing is, with the 7700K, the 7700K has so few cores, it can't actually generate as bad transients as like an 8700K or a 9900K. So, you know, it's just like, if with an 8700K the transient response isn't that bad, then on a 7700K it's probably completely a-okay, because the 7700K pulls, you know, 2/3 of the power an 8700K does. So that's kind of that. Anyway, the power stages here are a bunch of IR 3553s. More like a ton of IR 3553s, because they're everywhere. There's IR 3550. So all of the iGPU power stages, IR 3553s. The SA, more IR 3553. The IO, of course, another 3553. And we'll get to other voltage regulators that are also more IR 3553s. Anyway, the 3553 is a 40 amp POW IR stage. And the thing about, like, I don't really, like, from an efficiency perspective, this VRM is actually kind of a disaster. It can handle a lot of current, but it really doesn't have a very high peak efficiency, because the peak efficiency of the IR 3553 is a little bit over 92%. For comparison, if you wanted like a really high-end 50 or 60 or a 70 amp power stage, you can get parts that go up to, you know, 93.5%, 94%, 94.5%. Like, this power stage, as far as power stages go, like, the peak efficiency is actually really quite low. And so putting 16 of them like this into a V-Core VRM, like, the heat that they produce is spread across a ton of surface area, and it's not going to run very hot. But it's also not going to be super efficient, because these power stages just generally aren't very efficient. So that's kind of the issue with this approach to building a VRM, where it's just like, the thing is, Gigabyte actually gets Gigabyte has piles and piles of IR 3553, so they really like using them. And so I totally get how this ended up becoming a thing, because they were like the thing is, the 7700K is not going to pull enough power to need even half of this VRM. But the thing is, with a high-end motherboard like this, the priority here wasn't building a a cost-effective or efficient, or like really the priority here was getting a bloody 16 phase onto the motherboard as cheaply as possible. And yes, this is definitely a cheap way to get a 16 phase onto the motherboard. You can definitely do, like, as far as VRM designs go, you can definitely do better than this. At the same time, you can't deny that that this is completely ridiculous overkill, and honestly would do a great job of powering even a 9900K, because it's just got so many bloody phases. But individually, each of these phases kind of sucks. Well, not kind of sucks. I'm being a little bit too harsh on the 3553. Like, this is still a lot better than, like, if you had your two discrete MOSFETs with, like, 6 milliohm RDS on the low side. But as far as, like the thing is, if we go by high-end motherboard standards, like, this really should have been, you know, like, if you had 10 phases of 60 amp power stages, you would honestly probably end up with better. Well, actually, not probably, definitely end up across, like, at the lower end of the current output range, you'd get better efficiency with a 60 amp part than a 40 amp part, even if you had less phases. But the thing here was make a VRM that just has a ton of phases. So that's what Gigabyte did. So anyway, the good news is you don't really need any input filtering, and it's not like there's a lot of it on that. There is there. Like, actually, yeah, there's no, this is one of the sort of design differences. So this is all of the bulk filtering for this entire VRM, where it's just like, see, now if this was an Asus motherboard, especially a modern one, you'd have basically like one of these per phase. Except there'd only be like 6 phases total. So, but still twice as many capacitors as what Gigabyte's using here. So, you know, that's kind of the thing, is just like, yeah, they've got a ton of phases. So it's got, you know, very little input ripple. And it's just like, well, you don't really need a lot of input filtering that way. But the efficiency on this really isn't great. Still ridiculously powerful. So 1.2 volts output voltage and 400 kilohertz switching frequency running off of 5 volts. This VRM will running on 5 volts. Because the thing is, the power stages run on a different voltage than the voltage that they're regulating into vCore. So they run on 5 volts, but they convert 12 volts into vCore. So running the power stages on 5 volts, which is what you normally run them on, because you get 5 volts from your from your 24 pin. This VRM is capable of pushing 160 amps while producing 20 watts of heat, which is, again, like, that's not exactly a stellar efficiency figure. But let's put it this way, a 7700K has a hard time pulling more than 100 amps. As in, like, you're at like 1.4 volts, prime 95, you know, with liquid metal under the IHS, to get even 100 amps into a 7700K. So actually, one of the things I really want to try do with this board is get it to run a 9900K. Do the try to do the coffee-like mod on it and get it to run a 9900K, because this VRM is honestly wasted on a 7700K. Anyway, going up 240 amps output, this VRM would produce about 33 watts of heat, which, again, like, that's a little over 2 watts per power stage, which is just like, you can probably get away with this with no heatsink on the VRM. Because it's just so, like, it takes up so much surface area, just because of how many phases it has. And so the thing is with that is just like, yeah, so this is more current than a 9900K needs, like, ever. And then 320 amps output. So this is like 9900K on LN2. There it would produce about 45 watts of heat. So this VRM is absolutely, like, it's very powerful. It's just not super efficient, because you can actually get VRMs that do 160 amps output with less than, like, well, with around 12 to 14 watts of heat output instead of 20. Right? Like, that's the whole issue with using a power stage that has a peak efficiency of 92%. Like, no matter what amount of current you're pushing through the VRM, the peak efficiency of the entire thing is never going to exceed the peak efficiency of the components making it up, right? That's kind of the issue here. And, well, these don't really have a very high peak efficiency. So, yeah, that's the one downside to this VRM. But still, I do think, like, on a, you know, like, it's not a practical VRM design, but I still think it's cool. So that's why we're talking about it. And well, it's not even cool. It's more like, I think it's just completely ridiculous, and that's why it's worth looking at. So yeah, that's the V-Core. Ridiculously insane overkill for a 7700K. Totally unnecessary, and honestly impractical with even in any other context. It's just not a practical VRM design. Like this, it's just like you would honestly be better off just building like an 8-phase with 50 amp power stages or 60s, or yeah, definitely, an 8-phase using 60s or a 10-phase using 60s would be much more efficient, but it wouldn't look anywhere near as impressive, would it? So that's kind of the logic behind this VRM. Then the iGPU, like, we're not even going to talk about it because seriously, like, nobody uses the iGPU on a 7700K. At least not if you buy a board like this. I hope not, at least. So, yeah, this is just, like, honestly totally unnecessary, but, I think after the V-Core VRM, this can't really be much of a surprise. System Agent and I/O are actually rather reasonable. And they use well, unfortunately, I'm not sure what that looks like it's probably a 3570. Because I'm not sure if that's a 35204 or if that's a 3570, but it's probably a 3570 because there's a 3570 for the memory power, which we're going to get to. But yeah, so that's probably a 3570, and you might be like, Buildzoid, you have the board. Yeah, but I reassembled the cooling system for the motherboard before I got around to like writing down what this component was. And so I don't remember, like, I don't know what this is, and I'm not going to disassemble the board again just to figure out what that is, because I don't actually care that much. Anyway, it's going to be it's a 3570 or a 35204. It doesn't really matter that much because it's only running as a 1+1 phase for the system agent and the I/O rail, which are the memory controller voltages, and those don't really need to push a lot of power. So 3553 is there, of course, because, Gigabyte evidently... There was no shortage of 3553s when assembling this motherboard, so of course they just used more of those. And that's the system agent and the I/O there. And then we've got the PLX rail, which is actually made up of 3 discrete MOSFETs. So I'm not sure exactly, like, I think these are the low sides for PLX. These right here. And then on the front side of the board, we've got this one, which I assume is just the high side. Like, that would make the most sense to me because, like, putting the low sides on the back makes the most sense. Anyway, because it makes more sense to have both of the low sides in on the same side of the board instead of one on one side and one on the other. Anyway, so that's the PLX VRM. I don't really the thing is you're not going to overvolt the PLX chip, and this is actually very substantial in terms of PLX power. Like, I've seen PLX chips powered with is it? No, it is. It is. I've seen PLX power done with 2 MOSFETs and smaller package MOSFETs as well. So, yeah, that just kind of needs to exist. I don't really care what it is. Anyway, let's talk about the memory power delivery. So this right here is not the standard single phase Gigabyte VDDR. So, if you've been seeing some of my recent Gigabyte motherboard PCB breakdowns, you'd know that every time we talk about the memory VRM, I'm just like, well, it's the standard Gigabyte, single phase VDDR VRM with a 4C06N high side and then 2 low sides of the same that are the same thing. This right here is very much not that. This is a 2-phase, and guess what these are? Of course, they're more 3553s. Yes, that's right. You need an 80 amp memory power rail. Not really 80 amps, right? 40 amp power stages can't actually do 40 amps practically, but you get the idea. Like, ridiculous overkill in terms of VDDR, controlled by this chip right over here, which that's a 3570 for sure. I did actually check that one because that one doesn't live under a heatsink normally. But that's running in 2+1 phase mode, and now you might be like, wait, so what's the +1 for? Well, I'm glad you asked. Guess what this is? This is a voltage rail that I don't normally talk about because it's honestly really annoying to find on motherboards, and it's made with tiny little MOSFETs, and it's hard to get their part numbers, and it doesn't, this rail doesn't provide enough power to really be worth worrying about. But that's another 3553. Yeah, Gigabyte at their best. And this rail is a VPP, is actually that's the VPP rail for the memory. This doesn't really need to provide any power whatsoever, but hey, we've already got a bunch of 3553, like we've got 4 unnecessary 3553s in the iGPU VRM. Why don't we stick another one onto the VPP rail, right? It won't really make much of a difference. Anyway, as you all know, I don't really actually care that much about memory power delivery because DDR4 doesn't actually pull that much power, at least not like server DDR4 does, because you can get like memory sticks that are 108 gigs of RAM on one memory stick, but consumer DDR4 doesn't pull anywhere near that much power. And so the priority with DDR4 in terms of overclocking is not how you power it, it's what you do with your trace layout between the DIMM slots and the CPU socket. And let's go take a look at the back of the board now. Well, let's go take a look at that. And of course, this being a 4-DIMM high-end Gigabyte motherboard on the mainstream Intel platform, this is a T-Topology. And you can tell it's a T-Topology because you can see how, well, that's a terrible T right there. But no, the thing is basically the whole idea of this topology is to maintain equal electrical distance between the DIMM slots relative to the memory controller. Now, the downside to this is that if you are only running one memory stick in each DIMM slot, you have this great big length of unterminated wire hanging off of your memory trace, and that really limits memory overclocking because it screws up the signal integrity. So you end up with pretty major issues if you, like, basically this board's going to suck at memory overclocking if you only have 2 memory slots populated. If you actually populate all 4 memory slots, then it should do a lot better. But and this is actually, I think, the main reason why I like the old Z270 and Z170 Gigabyte 4DIMM motherboards weren't very popular for extreme overclocking, because they're all T-Topology boards, and it's just like, if you run 2 DIMMs on them, you're just like, the topology is actually working against you. So you're much better off getting like a mini ITX motherboard and using that instead, because this memory layout just does not work for a 2x, like if you're trying to push 2x8, which is the sort of preferred memory configuration for extreme overclocking. This kind of memory layout does not work well for that. It works really well for like 4x8, 4x4, really anything where you have 4 DIMMs and actually have all of the slots populated, because otherwise you have that unterminated length of wire and it just doesn't work. So yeah, that's what's going on with the topology here. And I also forgot to point out there's voltage read points right above the DIMM slots right there, hiding over there. And the last thing I forgot to mention about this board is that you may notice that we've got a 4-way GPU PCIe slot set up, but there's no extra 6-pin power connector or Molex connector or anything to provide extra power to the PCIe slots, which is a problem because the 24-pin, depending on which variant you're looking at, which this is the high current variant of the 24-pin, and that's also the high current variant of the 8-pin power connector, so that is at least 480 watts. And if you have, well, more than, like, it's not relevant to discuss the higher current rating version of, well, the higher current limit of that connector, because you're never going to hit that limit with any CPU that you can actually stick into the socket. That this motherboard's compatible with. If you hack it to run a 9900K, then on LN2 you might actually care, like, this might not be enough, but otherwise, yeah, this... Actually, no, it would still be enough because the benchmarks don't last long enough to really cause any issues. That's kind of the thing, just because you, like... time and like how it's not only about overloading something, it's also how long did you overload it for, because it takes time for things to overheat and melt. So that's kind of that. But anyway, the 24-pin here has a maximum current handling capacity, well, power capability of 240 watts on plus 12 volts. This is a problem because your PCIe slots, you can easily end up with 4 GPUs that pull more than 240 watts. And that breaks your 24-pin. So normally on a motherboard like this, I would have expected to have like a 6-pin over here or somewhere along the bottom edge. Evidently, Gigabyte, for whatever reason, decided not to do that, which I do actually find like that. I do consider that an actual design flaw with this motherboard. Like, there should be an extra power connector, because otherwise, like, the 24-pin is not meant to handle this much PCIe power draw. Like, it's just not designed for that. So, yeah, that's the one downside with this board, is just like They crammed it with stuff. Like, they crammed it with phases, they crammed it with postcodes, and evidently it even has Thunderbolt, which I'm like, you'd have to actually check the I don't care about the rear IO on this board. It's mine. It's just like, and also you're probably not going to be buying it new. But like, they've crammed it with features, but then they just seemingly just ran out of space for, you know, the extra power delivery necessary for this many PCIe slots, which is just like, that's not great. That's really not great. Now, luckily, I don't actually plan to run this. Well, I did actually want to try 4-way. Like, if I get this to run a 9900K, I do actually want to try 4-way GPUs on this with the 9900K. For certain benchmarks, that can be a very, very capable configuration. The thing is, well, it's not really a priority to get that done anytime soon, but it is definitely, like, it is possible to get the motherboard onto a 9900K BIOS. At the same time, I'm kind of worried that it's probably going to suck at memory overclocking anyway. Or that it's just not going to, like, the BIOS isn't going to be, it's not going to have all of the necessary extreme overclocking support, which we do have. Like, I'm not sure if we have all of them, but we do have at least some of the extra voltage regulators necessary for pushing Kaby Lake and other LGA 1151 CPUs below minus 120 degrees, but there should be 5 of these, and I'm only seeing 3. Or at least 3 obvious ones. Maybe, like, that could actually be a regulator as well, and this may be as well. So, yeah, not 100% sure on that. But, actually, is there anything on... No, the back of the board is actually surprisingly empty. So, yeah. But that's the Z270X-Gaming 9. I guess I can't really complain if they don't have all the extreme overclocking regulators, because it's like it's a Gaming 9 board, not an OC board. So... You know, it's just like, well, it's meant for gaming, and that's why it doesn't have that. And it's just like, well, that's why I don't like the board as much. But still, I think this is kind of one of, like, I did want to just take a look at this board because, well, it's a cool board in my opinion. I mean, it's not the best thing ever. You know, like, I really think it should have extra PCIe slot power. It would probably, like, I would prefer, well, the funny thing is for actually, like, the intended use of being like a high-end daily motherboard, the T topology just makes more sense because it works best for like 4x4 and 4x8 memory configurations. Right, and that's what you'd expect a high-end setup to use anyway. But yeah, it's just like, well, like, it's not an extreme overclocking targeted motherboard, so, you know, what am I complaining about? And yeah, that's kind of that. So yeah, it's a pretty ridiculous motherboard, right? And compared to a lot of the well, yeah, honestly, these days Gigabyte motherboards are a lot better. Like, well, not really. They still do the thing where you just have like a 16. Well, they don't do 16-phase VRMs built of 92% efficient power stages. They use power stages that do almost like 94% plus efficiency. So, you know, then it's like, okay, at least under some circumstances it can hit its peak efficiency. But this just has a low peak efficiency in general. So, yeah. Anyway, this is just a motherboard that, you know, is in my collection, and I think it's kind of neat. So I figured I'd do a video about it. Hopefully you found it interesting. And yeah, that's the end of the video. So thanks for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. And if you'd like to support what I do here with actually hardcore overclocking, I have a Patreon where you can support me directly. There's a link to that down in the description below. And then there's also the AHOC Teespring store where you can buy shirts, stickers, posters, and, you know, various other AHOC merch. That also helps out immensely with running the channel. So yeah, if you'd like to, you know, support the channel through buying some of that stuff, there's a link to that down in the description as well. And yeah, that's it for the video. So thanks for watching, and goodbye.